continue. I apologize. So, the geometry meaning of this is as follows. If this is a surface and we have a tangent plane, right? So this is a sigma u and that's a sigma v and that's a sigma, okay? Okay, and open set here. And in case if the determinant of Jacobian is negative, what does that mean? That means if this is another one, okay, regular surface patch, it's also you have U2 down, V2 down here, right? Then this time, U2 down maybe, this is maybe U2 down and with respect to U. Then the one U2 down, V2 down is not going to be, it's not like you get it from rotate counterclockwise. Actually, maybe this will be the U2 down, V2 down, okay? So then the cross product of those two, they have the opposite direction, okay? So this gives you, the sigma gives you this normal vector, right? And then sigma 2 down will give you this normal vector. Okay, this is determined by sigma 2 down. Okay, this will be determined by sigma. So maybe I call this plus, that'd be nice, minus. Okay, they have the opposite sign. Okay, this will be determined by, this is defined by, yeah, I don't say define, we should determine, okay? This is defined using the, yeah, if this is going to be sigma u, sigma v, and this will be the sigma u 2 down. Okay. Now, so if you choose a different regular patches, then you have a regular surface patches, and you possibly end up with the two opposite normal vectors. Okay. Now it's very natural to define the following. So if, okay, here's definition. When a manifold is called orientable, okay. If the manifold has orientation or orientable, it's by definition you can find a set of what I should say. You can find a set of regular patches cover the whole surface, such that the Jacobian between them has always a positive determinant between them. Okay? So here's the definition. Right? When we say S is orientable, right? If, okay, there is an atlas A for S, okay, with the following property such that if phi is we call the transition map between any of the two surface patches, then the determinant is positive. Okay. Now this guarantee, the normal vector you define using regular patches in this A, this guarantee you get a normal vector, smooth normal vector over the whole surface. Okay, so this guarantee the existence of a smooth normal vector field on the whole S. And how to define it? You just it's defined by always defined by any point, right? Any point on the surface, you choose a sigma, but that sigma you always choose from this atlas, okay? And then use at every point, right? And use this sigma, n is going to be sigma u cos sigma v divided by, right? And this is well defined. The reason is if you have another, if this is another one, okay, there are so many choices here. Okay, if another true that it's also from this, right? Then because the Jacobian has a positive determinant, so it's guaranteed no matter who is going, which regular surface path you choose, you always get the same vector because this is guaranteed, this is a positive. Okay, so you only consider regular surface patches from this atoms. Okay, so all the key point is just there's exists an actors, okay, such that the any of the transition map has a positive determinant, Jacobian. Then this n is well defined. Doesn't matter which regular surface patch you choose from A, and you always get the same normal vector. And this normal vector is smooth on the man, okay, on the whole surface. Yeah. And orientable, if only if you can find this. It's obvious to see. That. And there was a two. It's guaranteed as a smooth normal vector field. Okay. So actually, conversely, this is also true. It's two equivalent. Okay. If you have a smooth normal vector field over the whole surface, then you can always find an atlas with this property. Okay. Now, existence of a normal vector field means you already have the you can tell which side is positive, okay, which side is negative, the surface, okay, because which side is positive? Well, the normal vector, the direction of the normal vector on this side is positive, right? So given a surface, if you have a smooth vector field, then this side you can say it's positive, other side is negative, okay, right? You can use a normal vector field to tell which side of the surface is positive, which side of the surface is negative. Okay, so this is a normal vector field. All right, I'm going to talk about one example. This is a very famous example. This is called the Mobius Pen. Okay, how to define the Mobius Pen? It's defined in the following way. This is x, y, z plane, and have a circle, horizontal circle, okay? What I'm going to do is start from here. I use one piece of, just one piece of line, okay? And first, I'm not going to give you the Mobius Pen. I give you the standard one. Suppose you put a fence along this circle, right? Going like that. So what do you get? You get a surface, right? This surface looks like a cylinder. So what you get is it's like a cylinder, right? Okay. So this surface S is clearly oriented. S is first of all, S is orientable, okay? And you can always find a normal vector from this, okay? You find a smooth normal vector over the surface. Okay, this is a oriented, this is cylinder. Now, my next example is about Mobius Pen, okay? Y and X. Okay, so here's still circle, but this time I'm going to gradually twist it. Okay, so I'm going to put this one so you can see that why it's I just twist it around. Okay, so actually it's going down right now. So opposite side. Okay, so this side is a flat, and when I come back, I totally get different orientation. Okay, so this is still a surface. Yeah, it's a surface, but this surface is not this surface S. S is a surface. Okay, is a surface. No question about that. It's a smooth surface. Okay, but not orientable. Clearly, right? In anything. So you cannot tell which side is positive. If you walk around, yeah, this is a surface. If you walk around, yeah, it's harder to draw for me. You know, I don't know. Yeah, it's twisted. Okay, a twist. Okay, so it's harder to tell which side is positive. If you walk around the circle, and this side you walk and coming back, it's already inside. Okay, you are inside. You're not outside. So you actually to the back side. You know, if you are here, you begin with yeah. If you are here and you walk around and coming back, and then you to the same starting point, and actually you are on the other side. So this is not orientable. Okay, and this is a good example of non-orientable surface. Okay, so not every surface can be orientable. Okay, Mobius Pen is a famous example, and you can, okay, you can find a surface. I can find, yeah, at least find one surface patch, regular surface patch for the Mobius Pen. Okay, so sigma is U. I cannot find a single because this is a surface. Yeah, not every surface can be found. Can be covered by one single regular surface patch. Okay, those are three, and so I can determine the U second. Determine the open set a little bit later. Okay, so here's a 1 minus t sine half of theta. Okay, cosine theta, that's the first component. 1 minus t half of theta and sine theta. Okay, and the t cosine half of theta. Okay, so t is between, that's u. Okay, t is between, you can assume that's -1/2, +1/2. Okay, and the theta is between 0 and 2 pi. Okay, so what you get here is almost cover the whole Mobius Pen. Okay, if you cut it here, yeah, if you cut it this side, yeah, so you open it and you just twist it. Okay, so except of the vertical line, so this completely cover the whole. Yeah. This sigma, okay, the image of U is going to be the Mobius Pen except for the excluding the vertical line. Okay, is S excluded the vertical line. Vertical line. Let's see when when theta is 0. When theta is 0, it is going to be 1 and 0 and t. Okay, so that's a vertical line. Okay. Okay. But for this this surface, this is a surface. This is a surface regular surface patch, right? So let's find the normal vector determined by sigma. Okay, let's find the normal vector field determined by sigma. Okay. So you have to do the computation. You differentiate with respect to t, then this will be negative sine half of theta cosine theta, and negative sine half of theta sine theta, and the cosine half of theta. And sigma theta, okay, when differential theta, well, this is yeah, this is a little bit complicated because it's a product of two terms here. Okay, so let's do it. And when I different, it's negative sine theta, I have two terms. And what I should do, okay, let me do this one. That's two terms. Yeah, differential with theta, and it's going to be defined inside. It's half of t cosine theta, and minus 1 minus t sine half of theta sine theta. So that's the first term. Okay. Second term is a negative 1/2 cosine half of theta sine theta, and plus, and that will be cosine theta, right? And then this will be negative t sine half of theta divided by 2. Okay. Now this three components here. Okay, we have to look at the cross product. And when you look at the cross product, and yeah, how do we simplify a little bit? I run out of space. Okay, I ran out of space. So I'm going to calculate this, okay? Yeah. So yeah, let's do this, all the computations. I'm going to say AI plus BJ plus CK. I'm going to compute each of them, okay? So for the A, okay, this will be the cross product. Oops. Okay, it will be half of t sine half of theta sine theta. Okay, that's a minus, so be plus cosine half of theta square 1/2 and sine theta. Okay, after simplifying, it's just equal to where's I'm supposed to have a t here, right? And yeah, cosine this, and this is a derivative. That's a t here. Okay, that's a t. Okay, so that's a t. Okay, and plus 1 minus t sine half of theta cosine square half theta. Okay, so this is a as a cross part. Okay, this is a minus, so this will be minus. Okay, so here the first term will be half of t sine theta. Okay, and then minus 1 minus t sine half of theta cosine square half of theta. Okay, and then the b. B is going to be this is the cross product. Okay, then that will be half of t sine half theta cosine theta. Okay, and this will be the first term plus half of t cosine half theta and plus 1 minus t sine half of theta sine theta. Now I have so this will be actually, it's a negative of all the terms, okay? So this will be half of t, I think this will be cosine, I'm missing the cosine theta here. Yeah. This is a cosine theta. This cosine theta. All right. So those terms are pretty similar, right? Yeah, it's minus. Okay, let me check. This is the product. Yeah, this must be positive. Okay, then C. Okay, C is the last term. Yeah, it's going to be negative sine half of theta. Okay, it's harder to memorize all the terms. Okay, half of theta and cosine theta. Yeah, cosine theta. So it's negative, negative become positive, yes. Okay, this is a t sine theta. Minus sine half theta cosine theta 1 minus t sine theta and cosine theta. Okay, so that's the first part. Second part will be the minus sine half of theta cosine theta. Now this is not still sine theta. And then this will be half of t. Okay, I have to give up this computation because my screen is too small. I cannot memorize all the variables. Okay, so what we trying to do here is you can get all the formula, right? But what we get here is you get a normal vector. Okay, you get a normal vector. It's not worth it to compute. Then you can show that. Then you can show that the normal vector, the limit as theta approaches 0 from positive side, and that is going to be a negative 1, 0, 0. Okay, and however, when theta approaches 2 pi from negative side, that's going to be positive 0, 0. So what does that mean? is on the surface here, maybe looks like a fine. Then there's a twisting here. So when the starting point, the normal vector is a point to that direction, and then when you come back, the normal vector will be pointed to the other direction. Okay. So for the whole surface, you are not able to get a globally defined smooth normal vector. Okay, and when you glue them together, you find out that they're completely opposite direction. If you use this regular surface patch, and you do have a bunch of normal vectors, when you're coming back, it twists around. Actually, the normal vector becomes it's pointing outside. Okay, so at the beginning it's pointing inside. Okay, when you're coming back, it's because there's a twist. Okay, twist there over there. So this is why it's impossible to normalize it. Okay, it's impossible to get it's impossible to get a globally defined normal vector field. Of course, it has to be smooth, otherwise, right, on the whole surface. Okay. On the whole surface. So this is a typical example we always want to use it to discuss. Now let's talk about examples of surface. There are many examples of surface. For example, surface can be defined using the following equation, some example. The sphere, right? The sphere we can define by this equation, the traditional equation, right? So the sphere can be viewed as the level set, or what kind of level surface of the function f. Okay, it can be viewed as a level surface of the function f, and that function is just x squared plus y squared plus z squared. Okay. Okay. Namely, equals what? I want to talk about the following important theorem. This guarantee the level surface. We want to know when the level surface is indeed a surface. Okay, this is from calculus. This is a very important theorem. Okay, let f be a smooth function on some open domain W. Okay, in R3. Okay, so this is W, right? W, some domain, two-dimensional space. Okay. Okay, so here's the point. If the gradient of f is not going to be 0 for any x and y, z in the level surface, in the level set, then this is a surface. Level surface doesn't mean it's a real surface, right? Level surface determined by f equals constant. Okay? Then the level surface is a smooth surface. Okay, it's a smooth surface. So the level surface like that, it's the inside, right? Okay. And so what is gradient? Gradient of f, x, y, z is going to be a vector, right? It's a partial derivative of the function. Right? It's partial derivative of the function. This is gradient. Actually, the gradient of function also has a geometric meaning. The gradient of function is a perpendicular to the tangent plane at every point. And more important, yeah, the gradient of function at every point is a perpendicular to the tangent plane, right? So P here's a P is a point x, y, z, okay, in the surface. Okay. Now, how do you see that? This is why this is a perpendicular. Then you get a normal vector, right? For level surface, you don't need to find the regular surface patch, right? You don't need to find the regular surface patch. You can you can compute the compute the normal vector. Right? How do you do that? Okay, why? Well, I just need to prove this. Okay, so you let gamma. Okay, so yeah. Let me say S is going to be x, y, z, the level surface. So f x y z is going to be k. Okay, so this is a set. Okay, and then let gamma t be an arbitrary curve in S. On S, yeah, we say on S. Okay. So that means f gamma t should be always equal to constant, right? You value along this curve. So when you differentiate, you get fx, okay, fx, so fx, if you ignore the input variable, simply you can express by the channel, right? So x prime, fy, y prime, fz, z prime equals 0, right? So at the point P, which is x 0, y 0, right? Then, and this above notation can be written as gradient of f that is a dot product. All right, so this is a tangent vector. Tangent vector to the surface at the point P. Right. So tangent vector is arbitrary, right? So therefore, this concludes that this is a perpendicular. Okay, this is it's perpendicular to the tangent plane. And so you can use that to find the normal vector field. So then what does that mean? that means, yeah, so this is, we get globally defined smooth normal vector field on the surface, on the level surface. Okay, right, so define like this. At every point, okay, it is going to be the gradient of f. Okay, evaluate at x, y, z. Okay, where p is a point x, y, z in the surface. All right, so that means level surface, smooth level surface are always oriented. Actually, even has a singular point. Right, remove the single point, then you get an oriented surface. Because away from that, right, you have a uniquely, yeah, you can well define the normal vector field. Okay. So my conclusion is, every smooth level surface is orientable. So that means the Mobius Pen cannot be viewed as level surface. Okay, so not all the surfaces are level surface in R3. Okay, not all the surfaces are level surface. Okay. So let's take a look example. Okay, f x y z equals x squared plus y squared minus z squared. Okay. Then the gradient of f is 2x, 2y minus 2z. Okay. So this in general is not going to be 0, right? So this is not going to be 0 when x, y, z is not going to be 0. Okay, right? So if we consider, yeah, let's consider this surface. The special case, let f be, where's my erasable? So I'm going to consider that as x, y, z, okay? F, x, y, z. Okay. Now equals k. So let's put a k here, right? So if k is not going to be 0, okay, what do you get? If k is not going to be 0, then any point on the level surface, they're not going to be for any, yeah. So then x, y, yeah, just take a look at this point, right? If this, right? Yeah, for any at any point, I should say at any point. I know that this cannot be the origin, because if it's origin, then the value of f is going to be 0. So this implies the gradient of f is not going to be 0 vector. Okay, so therefore Sk is a smooth surface. Okay, it's a smooth surface. Now what happens if k is 0? If k is 0, okay. If k is 0, yeah, we do have one point passing through this, okay? So the S0 contains the origin, okay? Okay, if we remove this origin, okay, so at any x, y, at any point, which is not the origin, okay, and the gradient of this point is not going to be 0, okay? So what you can say? You can say that away from the origin, this is a surface, okay? So at least you can conclude that this is a smooth, it is a smooth surface, right? Okay, it's a smooth surface. And the level surface itself has a singular point. Right? Actually, the picture looks like that. So this is a single point. And if you delete that point, you get two regular surfaces. Okay? And they're oriented. You can tell which side is positive, which side is negative. Okay, use the gradient. Okay, so level surface, as long as a smooth surface, they're always oriented. Okay, yeah, you can talk about, you can tell which side is positive, which side is negative. Yeah. I apologize. It was interrupted.